In this session, we will be discussing how to determine the rate limiting step. See, rate limiting step of catalysis, right, between adsorption, surface reaction and desorption. See, we have first it is A to A dot S, next it transformed to B dot S, next it is B plus S, B is in gas phase. So, this is adsorption. We have surface reaction and desorption, right. So, here the rate is minus RAD, RS and minus RDC. Now, at steady state what happens? You see, definitely the rate of adsorption, rate of surface reaction and rate of desorption must be same. So, we can write minus RA prime is equal to minus of RAD minus of RS minus of RDC, right. Now, out of that which one is the rate limiting or the slowest step, okay. So, in order to understand that, we go for an electrical analogy. We have as if a circuit, we have a resistance to adsorption, then resistance to surface reaction and resistance to desorption. Right? And this I is the rate. Now, you see, if this potential we apply here, this E, then E is related to I for considering ohmic resistance as RAD plus RS plus RDC, and that is equal to I. So, if what happens, if RS or RAD is much larger than RS and RDC, we may simplify this overall rate minus or this I to be nearly equal to E divided by RAD, right. So, this adsorption becomes the rate limiting step as the corresponding resistance is pretty high. So, that is the approach which was originally introduced by Langmuir and Hinshelwood. So, that is why this is referred as Langmuir Hinshelwood approach, right. So, we will follow this approach basically to calculate the rate expression if I have adsorption to be the rate limiting step or alternatively the reaction to be the rate limiting, and finally, if desorption is the rate limiting step. So, this is our this objective to understand here this Langmuir Hinshelwood kinetics. Sorry, Langmuir Hinshelwood approach. So, for this purpose we consider the decomposition of cumin into benzene and propylene. Benzene is B, propylene P and cumin C. So, the reaction is C giving B plus P. Right. So, if we think of these intermediate steps, first we will have the adsorption of cumin onto the active side, cumin in the gas phase plus active side giving C dot S. So, here the rate of adsorption is Ka I am using, okay, yeah, Ka. Pc Cv, there is a forward reaction, C dot S by Ka. Next we have the surface reaction. C dot S giving B dot S plus P, I think. Yeah. This is the surface reaction step. P is liberated in the form of gaseous product. So, minus of Rs, Ks, C of C dot S, C of B dot S, Pp divided by Ks. And finally, the desorption. B dot S, B plus S. So, minus of R dC equal to Kc, yeah, Kc, yeah, Kd I am writing. Kd C of B dot S minus Pb Cv divided by Kdc. Now, Kdc desorption, this can be written Kdc dB, I have written Kdb. And this is Kd Cb dot S Kb into Pb into Cv. Right. So, these are the individual rate expressions. Now, first let us think, if adsorption is rate limiting, next what will happen? What will be my observed rate expression and how we can finally justify this through experiment, that this is adsorption controlled. If the reaction is adsorption controlled, so what will happen? You see that minus of RAD at steady state RAD equal to minus of Rs is equal to minus of R dC. However, Ka, the rate constant, forward rate constant for adsorption is much less than Ks and Kd if adsorption is rate limiting. Right. So, if adsorption is rate limiting, then Ka is much lower than the forward rate constant of surface reaction and desorption. So, minus RAD by Ka is much higher than minus Rs by Ks and minus RDC by Kd. So, these we can approximately assume relative to, so in comparison to minus of Ra divided by Ka, Ad by Ka, we can simply drop these two. Okay? So, if I have dropped this, so we have C of C dot S is equal to or is equal to C of B dot S into Pb divided by Ks, and C of B dot S is equal to Pb into Cv into Kb. Right? So, you see, if you replace this B dot S here, yeah, it is Pp, this is Pp, yeah. So, if we replace this Pp by Ks into Pb into Cv into Kb. Now, the side balance, active side balance, what it will give you? Ct is equal to Cv, the free, then Cb dot S plus Cc dot S. So, we have Ct equal to Cv plus Cb dot S. Cb dot S is this, Pb into Cv into Kb plus Pp Pb into Kb by Ks into Cv. So, Cv can be expressed as Ct by 1 plus Pb Kb plus Pp Pb Kb by Ks. So, we have to get the Cv expression and Cc dot S expression in order to get this RAD. So, minus of RAD, which will be now equal to minus of Ra prime, right. It is Ka Pc Cv minus Cc dot S. Cc dot S is this one, Pp Pb Kb Ks Pp Pb Kb Ks into Cv. So, if we replace that, I will get Ka Ct Pc minus Pp Pb Kb by Ks, and denominator it will be 1 plus Pb Kb plus Pp Pb Kb by Ks. So, this is the observed reaction rate. This will be the expression. Right. Now, the question is, if I have this expression, how we can experimentally justify that this, or we can experimentally outline some protocol by which we can understand that okay, adsorption is rate controlled step. So, initially you see there is a big expression here. Initially PP and PB are 0. We have only PC equal to PC naught, right. Only Qmin is there. So, this term 0, this is 0, this is also 0. So, minus of RA prime 0 is equal to Ka Ct into PC naught. So, that is a direct proportionality exists to initial partial pressure of Qmin. So, that is the hypothesis. So, if adsorption is rate controlled, so the initial rate of the reaction, right, will be proportional to the partial pressure of Qmin. So, if I plot this initial rate with respect to the partial pressure of Qmin, I must get this sort of data, right. So, if it is something like this, say if we have conducted this reaction with 3 or 4 initial partial pressure, changing the initial partial pressure of Qmin, and we have got this proportional relation. So, we can confirm that okay, this is simply the adsorption control system. Okay. So, similar to this adsorption control system, we can think of the same system may be surface reaction controlled. So, if it is surface reaction controlled, what will be the rate expression? So, let us finally find out that if it is surface reaction controlled, then what will be the rate expression in terms of the partial pressure and what will be the respective initial rate expression, right. So, if the system's rate is controlled by surface reaction, so in this case what we will have this minus of RAD by Ka and minus of RDC by Kd is much lower than minus of Rs by Ks, as Ks is lower, much lower than Ka and Kd, right. So, in this situation we said minus of RAD by Ka equal to 0 and minus of RDC by Kd also equal to 0. So, therefore, C dot S becomes Ka Pc into Cv and Cb dot S becomes Kv into Pb into Cv, right. Site balance will yield Ct equal to Cb dot S plus Cc dot S plus Cv. So, obviously, Ct becomes Cv plus Ka Pc plus Kb Pb this we can set 1 and we can put a bracket. So, we have CV equal to CT divided by 1 plus Ka PC plus Kb Pb. Right. So, we need the value of Cc dot S. So, minus of R S, Cc dot S and Cb dot S. R is equal to, which is equal to minus of Ra prime, sorry, rather Rc prime. We should write here, previously we shouldn't have written A, it should be C because the reactant is cumene. So, minus of Rc prime equal to Ks Cc dot S. Cc dot S, we have found that it is capital Ka into Pc into Cv minus the Cb dot S Kb into Pb into Cv into Pp by Ks. So, we have minus of Rc prime Ks into Cv Ka Pc minus Kb Pb Pb Pp divided by Ks. Now, substitute back this expression of Cv here. So, it is Ks Ct Ka Pc Kb Pb Pp Ks total divided by 1 plus Ka Pc plus Kb Pb. So, this is minus of Rc prime and that will be the reaction rate. See, there is a distinct change here from the previous rate expression. Now, if we think of initial rate, at t equal to 0, we have Pc equal to Pc0, Pb and Pp, they are equal to 0. So, this term is cancelling out, this term is also cancelling out, however, this will remain, this definitely will remain. So, minus of Rc prime is equal to Ks Ct Ka Pco divided by 1 plus Ka Pco. So, it is a kind of hyperbolic relation RCO. Right. Now, if Pco is much smaller, or Ka Pco, or Pco is small, let us say Pco is small, right. So, this term is negligible. So, we have minus of R prime Co is equal to or nearly equal to Ks Ct Ka Pco. Alternatively, if Pco is large, then minus of Rco prime, this term 1 can be neglected, then Pco is getting cancelling out, Ka is also cancelling out, Ks into Ct. So, this is constant, right. So, here minus of Rco prime versus Pco with this sort of curve, increasing and then saturating out. Okay. So, here you see this regime where it is independent, the Pco is large and minus of Rco prime is constant. Here Pco is small, minus of RCO prime is proportional to PCO. Right. So, that is the situation we have if the system is reaction controlled, right. The initial rate will follow a kind of hyperbolic trend. So, it will linearly increase initially for low value of PCO, and then it will flatten to some threshold value, right, for larger values of PCO. So, finally, we will think of if the system is controlled by desorption. Now, if it is controlled by desorption, then what will happen? So, here minus of R dc by Kd is much larger than minus of R ad by Ka and minus of Rs by Ks, right, as we have Kd is much smaller than Ka and Ks, and additionally we have minus of RDC, minus of RAD and minus of Rs, they are all same. So, we set minus of RAD by Ka to 0 and minus of Rs by Ks also to 0. So, from here what we will get? C dot S is equal to Cb dot S into Pp divided by Ks, and from this adsorption we have C dot S is equal to Ka Pc into Cv. So, Cb dot S we can write as Ks by Pp into C dot S. So, C dot S if we replace, it will be Ks Ka Pc by Pp into Cv, right. So, we have got the Cb dot S expressed as a function of Cv only, C dot S as a function of Cv. So, that is the only unknown, because Pc and Pp they are measurable term. So, next side balance. Ct is equal to Cv plus again Cb dot S plus Cc dot S. So, this is Cv plus Cb dot S, Cb dot S if we replace Ks Ka Pc by Pp into Cv plus Cc dot S Ka Pc into Cv. So, Cv, which is the unknown, that is Ct divided by 1 plus Ks Ka Pc by Pp plus Ka Pc. So, my rate of desorption minus RDC, which is minus of RC prime, it's equal to Kd within bracket Cb dot S. Cb dot S is Ks Ka Pc by Pp into Cv then minus KB, PP, PB into CV. So, this CV we can take common and substitute back the expression we have got. So, KD into CT within bracket KS, KA, PC by PP minus KB into PB, that divided by 1 plus KS, KA, PC by PP plus KA, PC. So, what's happening now? CB dot S. Okay, let me check. Probably I have got CB dot S. CB dot S is KS, CCS, CPP, KC, sorry, here we should have written KA or what. So, okay, no problem. So, if I replace CB dot S, is there any problem? CB dot S is replaced by this. CB dot S is KS by PP into CC dot S. KS, K, PC, PP, CV. KS, K, PC, PP, CV. Okay. Minus minus this desorption KB into PP into CV. What is happening? KB into PP, PB into CV. PB CV by KP, what I have mentioned as KP, PC, okay. So, if I take this 1 by PP common from here, so minus of RC prime is KD CT by PP KS KA PC minus KB PB PP, right, and denominator will be PP plus KS KA PC plus KA PC PP divided by PP. So, this cancels out. So, if I think of this initial rate, T equal to 0, PC equal to PC naught, PP and PB they are 0. So, minus of RC prime 0 is equal to, see, Kd, here it is Kd, Ct, Ks, Ka, Pc naught, because this Pp and Pb are 0. And denominator, we have this term 0, Ks, Ka, Pc naught. This term is also 0. So, this and this cancels out. So, we have minus RCO prime, it's equal to Kd into Ct, and it is independent of initial pressure, partial pressure of cumin. So, we have 3 different regime, you see, minus RCO naught divided by Pc naught, it will be a flat line. So, if it is flat independent of PCO, then it is desorption controlled. If it is proportional, throughout it is proportional to this initial pressure, initial partial pressure of cumin, then it is adsorption controlled. And if it is linear or proportional to this initial rate for low partial pressure and constant for high partial pressure, then it is surface reaction controlled. So, that is a typical example. We have demonstrated that how to get this confirmation regarding that whether it is reaction controlled or diffusion controlled or this desorption controlled. Sorry, this reaction controlled, adsorption controlled or desorption controlled. Right. So, we have another topic left in reaction engineering, and the only topic, that is the semi-batch reactor. Though I should have covered this much earlier, but let us discuss about the semi-batch reactor, its performance equation for a specific system, right. So, and that is all will be about reaction engineering theory. Next in this session, in the next session, we will be discussing the gate problems and in general the problems of reaction engineering. So, a topic here is semi-batch reactor. So, why we use this semi-batch reactor? Why semi-batch is necessary? See, I have a reaction A plus B giving T and U. It is a competitive parallel reaction, where this is the desired product and this is undesired, right. So, here the rate constants K1, A, B are the exponent of the rate constant. The order is A with respect to capital A and B with respect to capital B, and here it is this is say A1 and B1 and this is A2 and B2. So, this yield, this overall yield maybe, this overall yield of T with respect to U, or selectivity of T with respect to U. This is K1 Ca to the power A1 Cb to the power B1 divided by K2 Ca to the power A2 into Cb to the power B2. Right. So, we will not discussing about temperature K1, K2, let us keep it aside. So, Ca to the power A1 minus A2, Cb to the power B1 minus B2. This we have discussed when discussing the yield, right. So, if you see A1 is greater than A2 and B1 is less than B2, we have to maintain high concentration of A and low concentration of B. So, obvious remedy is go for semi batch mode. Right? A is there in the reactor and we slowly add B. So, you see what is the utility or why we have to go for semi batch mode. Next we will write the balance equation. So, here we are adding B, concentration is Cb naught, volume flow rate is V naught, right? Yeah, concentration is Cb naught, volume flow rate is V naught, and any other specification? Yeah, no. And this A is there at time t equal to 0, total is B naught and Ca is Ca naught. So, this is not a continuous form, it is a semi batch mode, right. So, definitely the volume will go on increasing with time. So, you can write this as dV dt equal to V naught and integration will yield V equal to V naught plus small v naught into T, right. So, that is our first equation. Now, second, this is outcome of overall mass balance, we consider this incompressible and from there we get this. And second is the balance of A. What is that? Input minus output minus consumption by chemical reaction is equal to accumulation. Now, input is 0, output is 0, and here the consumption by chemical reaction is minus of Ra into V, right. An accumulation term is ddt of Ca into V. So, it is dCa dt into V plus Ca into dV dt, right. So, it is minus of minus Ra into V is equal to dCa dt into V plus Ca into V naught. So, that is the balance for A. So, we have we can further modify this if we want to write that dCa dt equal to minus of minus Ra plus Ca into V naught by V. So, V is a function of time, right. So, it is the second equation. So, for B if we write the balance, inflow it is Cv naught into V naught, outflow is 0, disappearance, say it is reaction is A plus B giving product, and that consistency of the relation between minus Ra and minus Rb, that depends on the stoichiometry. Okay. So, anyway, let us write that here minus Rb, inflow minus outflow, minus Rb is positive because it is a reactant, into V equal to ddt of Cv into V. So, it is Cv naught into V naught, and this we can write as my plus of Rb is equal to V dCb dt plus Cb into V naught, right. So, if we divide this, no, we cannot do that, okay. V into dCb dt equal to Cb naught minus Cb into V naught plus RB. And simply this dCb dt, yeah, dCb dt, this Ra into V will be there. Sorry, I have missed that. V is there, RB into V. So, this is Cb naught minus Cb into V naught by V plus RB. So, this is equation 3. So, initially you see this Cb equal to 0, Ca equal to, so what will be the initial condition? These 3 are the outcome. This is directly a solved equation, otherwise we can take directly this. Okay. So, at t equal to 0, Ca equal to Ca naught, V equal to V naught and Cb is equal to 0. So, that is the initial condition. So, with that we can actually solve these 3 equations maybe numerically, unless it is an easy system like simple bimolecular reaction A plus B giving product, elementary bimolecular reaction. So, then we can attempt at least some sort of analytical solution. So, that is the utility, that why we should go for semi-batch reactor. I have explained it in terms of selectivity. This is called the selectivity, very similar term to that of yield. Yield is with respect to the desired product, or desired product by the amount of limiting reactant which is A may be consumed, right. But selectivity here, as it is bimolecular, we are writing it in terms of selectivity, and from there we can justify that why we have to go for semi-batch mode. And this is the balance equation for semi-batch. For any other similar system, you can also write and develop the same equation. So, that is all about the theory part of the reaction engineering. In this next session, we will be discussing problems of reaction engineering, whatever is there in GET and in textbooks.